Hello everyone, Mr. Tomashik here. Today I want to do a quick review of the atomic data we talked about last week and how we can calculate the averages for the atomic masses or atomic weights that are on the periodic table. All right, first let's do a quick little review here. All right, we have a data table that has a list of things we need to figure out, and if we are looking at our periodic table, we're going to fill this out for the element magnesium, which is atomic number 12. Atomic number 12. Now, what's the atomic mass? That would be this number right here, 24.31. And that's in grams per mole. Grams per mole, sometimes called the atomic weight. The mass number. Now, the mass number would depend on the isotope. Remember what isotopes are. They're atoms of an element with different numbers of neutrons or different mass numbers. This number right here then is the average of all the known isotopes. We'll talk about that here in a minute. All right, and it's not a whole number because of the average thing. All right, so if we want the most common isotope, we would round it to a whole number, in this case 24. So the mass number of the most common isotope would be 24. Now, how many protons? That's the same as the atomic number, in this case 12. How many electrons? The same as the number of protons, so in this case also 12. And the number of neutrons then, remember that the number of protons and neutrons added together must add up to the mass number. So the number of neutrons in the most common isotope would also be 12. So 12 protons, 12 neutrons gives us a mass number of 24. All right, so we can extract that data from this. The other numbers in here, like the +2 and that little box, that's stuff for a little bit later. All right, now, atomic mass. The atomic mass is a mass of 1 mole, but it's also the mass, the average mass of all the natural occurring isotopes. Now, what do we mean by that? All right, this chart here shows us the percent abundance for all the known isotopes for magnesium. All right, so we have magnesium 24, 25, and 26. Magnesium 24, 25, and 6. That means that some of the magnesium out there in the world has a mass number of 24, and some of 25, and some of 26. And it looks like most of the magnesium in the world is magnesium 24, and smaller percentages of that are the rest. All right, so when we say the percent natural abundance, this would be all the known isotopes of magnesium. Now remember, the one lab that we did, we took some magnesium and we reacted it with acid and produced hydrogen gas. All right, now how does one calculate averages? Now, the simplest way to do an average is just to take a sample of something. For example, here's the mass of a bunch of paper clips, and they're all pretty close to the same, slightly different. If we add them all up and divide by how many we got, so if we add them all up, we get 5.5, and if we take 5.5 divided by 6, 5.5 divided by 6, then we get our average of 0.92. All right, that's calculating an average. Now, you learn how to do that in math class. All right, add them all up and divide by how many you get. Now, doing that with a large number of atoms might be kind of difficult. All right, so we got to do it a little differently. All right, let's consider this example here. Here we have this molecular model kit. It has a bunch of marbles in it of different colors. We may look at that later down the road. All right, I took that box and I counted up all the different colors that were in there, and here's the data that I got. All right, I have 13 white ones and 4 red ones and 2 orange ones and so on, like that. The total number of marbles in the box then is 39. So I could calculate a percent abundance from that. So 13 out of the whole of 39 times 100 means that 33% of the marbles are white. 4 out of 39 times 100 means that 10.3% of them are red. and so on. And we could do that for each one of them. Notice that each case we're dividing by 39. All right, you take the occurrence of each one divided by the total, and you can get the percentage of each color. Of course, our percentages then should all add up to 100, all right, if we're doing something right, so we can kind of check. So this is what we mean by the percent abundance. Out of this whole sample of marbles, each one of these percentages applies to each one of those different colors. Now, we could do that with atoms too as well. Let's look at another example. All right, you're all familiar with marshmallows, and marshmallows can come in different sizes. For example, this bag of marshmallows here has all of the 3 different kind of sizes. We have the very large marshmallow. We have the regular average size marshmallow, good for roasting marshmallows. And then we also have the mini marshmallow. Now, in every case, they're all marshmallows. They taste exactly the same. They're made out of the same stuff, and they're just a different mass. All right, so we could consider them like isotopes of marshmallow. They're all marshmallow, but each individual piece has a different mass to it. So here's what I did. I took my bag and I massed out all the different marshmallows in there, and I got 2 grams, 14 grams, 22, 2, 14, 22. The big ones apparently are 22 grams. The medium-sized ones are 14, and the mini marshmallows are 2. Now, if I want to find the average mass of all these marshmallows, that could take a while because I got a rather large bag full of them here. All right, but if I could do this, somehow separate them into separate bags without having to count them all, I could find their percent abundance. Some of them being the 2-gram variety, the 14-gram variety, and the 44-gram variety. All right, so what I would have to do is find the mass of all of them first, and then the mass of the individual bags, and I could come up with data that looks like this. So I measured out the bag with the mini marshmallows in it, and I got a mass of 22 grams for the whole bag. I didn't have to count them, all right, but I did the same for the bag with the 14-gram marshmallows and the 44-gram marshmallows. So the big bag with all of them mixed together had a mass of 353 grams. Now, remember that I didn't actually count them. I just measured their whole mass in one big shot. So now I could find their percent abundance based on their masses. All right, the mass of the individuals divided by the mass of all of it. So these are all of the mini marshmallows together, mass, and the mass of all the marshmallows together, and that means that 34.6% of my mass is mini marshmallows with only 2 grams each. And then I do the same for the 14-gram marshmallows and the 44-gram marshmallows, and I get the percentage of my sample of each one of them. Now, to find the mass, I would use these weights. All right, I see these are the percentage abundance, which is the weight of each one. All right, or the abundance of each one. So if I take the mass of the small marshmallows times its abundance, I get a number. If I take the mass of the medium marshmallow times its abundance, I get a number. And then the large marshmallow times its abundance, and I get a number. Now, when I add all these together, I get the average. All right, doing it this way is called a weighted average. All right, and the weight is the percentage of each one. All right, now to do this, I did not count the number of marshmallows. I measured the mass of the marshmallows and took the mass of the individual part divided by the whole to get a contribution for each case. All right, now I don't necessarily have to write each one of these down. I could just do 2 times 34% plus 14 times 25% plus 44 times 40%, and then hit enter, and I'll get my answer. All right. If I want, I can write down these contributions each time and add them up. All right. Now, when you do an average this way, you don't add them up and divide by the number of them you have on there, because the percentage is taken into account that. So we just take the mass of the individual times its abundance, a percentage. Now when you punch that in, remember 34%, 34.6% would punch into the calculator as 0.346. So when we punch that into the calculator, we have to take that into account as well. Okay, this data table tells us the natural abundance as a percentage for the known isotopes of magnesium. All right, so magnesium 24 in nature occurs as 79%, and magnesium 25, 11%, and 26, 10%. Now, these are the only known isotopes. So how do we arrive at this number? Because that number is an average of all the natural occurring isotopes. All right, we'll take the 24 mass number times its percentage. Now, in the calculator, I would put 0.7900. All right, now for that, I could get a number. I could take my 25 times 0.1100 and get a number. I can take my 26 times 0.1000 and get a number. However, I could just do this all in the calculator in one shot. 24 times 0.79. Let me grab my calculator. 24 times 0.79 plus 25 times 0.11 plus 26 times 0.100. And I get 24.31. 24.31. So when I take the natural abundance of all the known isotopes of magnesium and find their weighted average, that's how I arrive at the number that is on the periodic table. So that's an average of all the known isotopes of magnesium.